now I'm going to get to the good stuff, as Curtis said. We're going to do some image processing examples. So we have sort of 5 workflows. Basically, we're going to take a look at n-dimensional images and crop them. We're going to do some segmentation. And this example is kind of cool because we're also going to go back to the ImageJ1 world and do a little bit of analysis. Then we're going to threshold a hyperslice. So we're actually going to, again, use some of the ImageLib utilities to that are wrapped by ops to do some kind of cool partitioning of what exactly we're thresholding. Then we're going to look at projections. And this was actually a listserv question, so that's kind of cool. We can, it was driven by the community. And then if we have time, we're going to look at a FFT template matching example. So the first example is the cropping example. So if you guys go to templates, go to tutorials, you're going to see a crop confocal series. So hopefully everybody can open that. And then you're going to want to open samples and open the confocal series. So we have a 4D series here. And I'll just step through what this script does. So we're going to look at data using the ImageJ2 data model. We're going to see what size of dimensions we have. We're going to look at what type of dimensions we have. And then we're going to actually do some cropping. So once you open up your script, you should see this. And the first few lines of this script just set up the parameters that we're going to need and perform some imports. So you should understand that by now. So we import the ops service and the UI service and the input data set. Then this step is kind of important. We actually loop through the data set and print out the dimensions and then assign them to variables. So when we're dealing with multidimensional data, this is sometimes sometimes we're not sure how the data is organized. So sometimes it's a good idea to run a little code snippet like this to see what kind of axes we have and what order they're in. The data model has some nice utilities to retrieve axes information by name. So we can write, this is kind of important here. So we can write, this allows us to write code in a way that should work on any kind of data set, even if the dimensions are mixed up or something. So if you see this little piece I'm highlighting here, that's actually telling us the index of the x dimension, the index of the z dimension, the index of the channel dimension. Yep.
How do all these commands know that you're referring to image? IMG is where you get the image plus, but all the loop and also the x-line and all that, those things are in reference to IMG.
Okay, so that's a really good question. Let's go back a step. So what I did here is my parameter is called data. So we have a parameter called data, and then from the data, IMG is the image that data contains.
This is kind of an implementation detail, actually.
Yep.
When we first wrote this script, we used data parameter. We didn't use IMG. So the data set is your image, okay? But there's a bug right now. The data set is actually wrapping another object called IMG plus. So the fact that we have to use IMG in some places is actually to work around limitation.
And it's
Yeah, we only asked for
Numberable
one, so it would be the
series.
axis.
Numberable series is what we open because that's the guide, it's active, that's
Yeah.
what's going to stay in there. The fact that we have data and IMG is unfortunate, and that's not the goal because you want to have to essentially unwrap it in some
And supposing I get images,
then you put two in
Yep.
that data set and one that data set two, and then it wouldn't, right? Because there's no such thing as two active images.
So then the next step of this script is that we actually use ops to crop data. And if you look at this call, you'll see that we're actually using a utility. We're passing this crop function an image, but we're also using a utility to basically create a very simple ROI. So this little intervals.createMinMax takes a starting point and an ending point, creates an ROI, then the crop function will extract that ROI. And then the final step is we just use our UI service to actually show the cropped images that we created. So if we run this, we should see a bunch of new cropped images appear. And we also see some information printed out. And that is that information is printed out from this little code snippet here. So it tells us what type of axes we have and the size of them. So here's a quick exercise, and ask me questions about this if it's not apparent how to do this. Can you change the code to make a crop that we haven't done yet? Crop slice 15 at channel 2. So the first thing I would do here is I would copy a previous code snippet that crops. Just assign like a simple variable here. New is probably not a good idea. New im, it's a little better. Name new. And also add a line of code to show it. Now, the question is, how can we change this to perform a different crop? So I'm actually going to copy this line here because it's the most similar to what we want to do. It's cropping channel 0 at z equals 12. So we want to crop now, this time we want to crop channel 2 and slice 15. So when you're creating these intervals, it's just a starting point and an ending point. So the first 4 parameters are the starting point. The second 4 parameters are the ending point. So this says start at 0, 0, 0, 15, and end at the end of the data set, at the end of the x dimension, end of the y dimension, 0 and 15. So this is sort of inclusive. 0 to 0 means crop out just 0.
So this crop parameter implicitly assumes you have 4 dimensions and then x and y. Do you guys have any plans to extend this for eventual n-dimensional data sets where it's actually literally unbounded the number of dimensions?
Yeah, definitely. And Curtis,
You're talking about Like,
Like
this
it's
crop
not a
command is-
polarization axis. in
This
there,
crop
is it?
command is n-dimensional.
Yeah.
The only 4D bounds here are that he's creating this crop interval in 4D because he knows the data.
Yeah, because I know the data is 4D.
Oh,
so
okay,
But
yeah,
like you
so-
could write a for loop
Yeah, yeah.
or whatever here
Yeah.
to loop over dimensions, create
Okay.
an interval, and set the values somehow. You kind of have to
Yeah.
know what bounds you want to crop.
Sure.
Like for
Yeah.
example, we could generalize this
Mhm.
right now with the current code.
Yeah.
Crop -1 on all dimensions, right? But
Okay.
it would be harder to understand.
Sure.
yeah, it would be hard.
Yeah,
Yeah. So yeah, it's great. It is.
So yeah,
There's that intervals thing in there. Have those as correct parameters as well.
so this little loop here that just printed the data, that could, like, instead of printing the data, you could use it to create your intervals, right? So you have the number of dimensions, you have the indexes as the dimensions and stuff like that. So you could create a fancy loop that's very n-dimensional, robust. So anyway, this little example here, we know the organization of the data. So we change this code here to crop out channel 2 and slice 15. And then if we run it, okay. So what happened? What happened there is the active image changed, and it didn't have all the dimensions that my poorly written script was expecting. So go ahead.
So one question. So it looks like you're displaying the crops of
Yeah.
Is this really the case? So is the data set itself two-dimensional, or is this
The data set itself is
the data set?
the crop data set. Actually, I don't know. I'd have to print it out because I know it's supposed to be reduced to be two-dimensional, but sometimes you end up with like dimensions with length 1.
Just throw a number on there and see on dimensions. Because everything's coming back as input stuff, right?
So
So all he has to do is write.
Yeah, I mean, it's
Then
directly
that
based
number.
on if you start to drop all of those intervals.
I don't remember. Might
just quickly getting too much open here. So
This is actually a big topic of the hackathon is lazy ops versus like, do you just make a view or do you do some
so it is 2. Yeah. So it did reduce it. I actually just tested that, and I think it does work correctly. I think it does. Because I ended up I was trying to do some fancier crops, and I ended up with like a Y, Z, C section. The only problem with that was it doesn't display yet because it doesn't have an X dimension. So I think ImageJ1 wasn't expecting something without an X dimension. But yeah, I can update this example. Like I was actually working on it just because of a question that was asked, and I can update it to show like an XY C or something like that. Okay, so that was the first example. Any other questions about that example? Okay, so the next thing we're going to do. I think this is a really, really important example here. Maybe the most important one, because we're going to segment an image, and then we're going to use some of the classic ImageJ1 functions to, display a results table. So in the future, there's going to be ops. Ops will be capable of have some more sophisticated results and ROI processing functions. So this will, in the future become outdated. However, I anticipate like there always being IJ1, like cool IJ1 utilities that you'll always want to use. Like even 5 or 10 years down the future, I bet there'll be stuff in IJ1 that you're going to say, oh, I've got this awesome ops script, but there's this one thing that's only in IJ1 and I want to integrate it. So this shows how to do that. So I think it'll be, once you can perform an op, go back to the IJ1 world, and then you can do any kind of IJ1 macro commands that you'd like. So we're basically, in this example, going to create a Laplacian of Gaussian kernel. It's a pretty, traditional sort of segmentation routine. We convolve with that kernel, then we apply a threshold, and then we analyze using ImageJ1. So if you go to your script editor, go to tutorials, open up this ops threshold IJ1 analyze. And while we're at it, select this image C0 Z12, select the Z slice and make it the active image, or close some of the other images just so when we run it, it'll process this image. So you should this kind of code should be starting to look familiar. We're setting up the parameters. Now, in this next step, we're importing some functions that we're going to need to translate between ImageJ2 and ImageJ1. So one question that I often get from people, when doing tutorials like this or lessons is, well, how do you know how to do this, right? So I guess it goes back to what Curtis said about, first off, about all the Javadoc and all the resources that are available. But it might not be intuitive. Like, how would you ever know that you need this class called ImageJ functions to do these conversions? So for something like this, like I think the starting point might just be the listserv, or if it's a more development-oriented question, the development listserv. You'll get, you say, hey, I want to go back to the ImageJ1 world. How do I do it? You'll get an answer pretty fast. And there's also some, if you're a GitHub user, there's also some really good conversations going on using a tool called Gitter. It's like sort of a chat for people involved in Git projects. So the next segment of this then uses ops to implement the traditional segmentation pipeline. We use this Laplacian Gaussian kernel. It's like a high-frequency edge detector that's combined with the Gaussian, so it does edges and noise at the same time. And then we apply an automatic threshold. And then the final step, we use IJ1 functions to analyze. And before we go through the exercises, why don't we try to run the script and see what happens. This is the ops threshold, IJ1 analyze. Make sure this C0 Z12 image is active. Run it. And I'm going to do that again. So run the script, and we have some interesting things here. We have this image called LOCI, which is the result of the Laplacian of Gaussian filtering, a thresholded image, and then a table that should look very familiar because it's the results table from ImageJ1. So some exercises here. First exercise, make sigma a parameter. So make the width of the filter that we're using a parameter. So what I'm going to do here is I'm going to use my parameterized scripting style.
Which sample image is this again?
Okay, so the sample image, the image that we've been using is the one called, it was created from the first script. So the easiest thing to do is, if you don't have it up anymore, just close every single image, run the first script, and then you should get this image. And and maybe save it if you don't want to regenerate it again. So yeah, if you guys are going through these tutorials and just getting like an explosion of images, just close everything and open up the confocal series sample image and run the crop confocal again, and you'll get the cropped images that we need for the next step.
Does anybody want more time to quickly do that?
Yeah, so anyway, I'll do that. So I'm going to go here. Now, I think Wayne mentioned yesterday there's a new shortcut to close all images. Oh, is there?
Yeah.
Shift W.
Yes.
So that's awesome. Shift W, then go to File, Open Samples, and go to Confocal Series. So we got our Confocal Series back. Go to our first script, run it. Oh, no. Huh. Oh, wait. I ran the wrong one.
Added a parameter at the top that isn't complete.
Yeah, I just had the wrong script highlighted. Just all this. This is the one I want, the crop confocal series, and I get some images, these images to work with, and we can actually. I think this Z012 works pretty good with the thresholding. And then if you want to avoid image explosion, just close all these guys. And then we go back to the ops threshold, IJ1 analyze. So what we're trying to accomplish here is to add a new parameter that's going to define the sigma of the filter. So we can go at double sigma, or let me just call it S for conciseness. And we are going to put a S in here. Yep. Okay, so increase the font size. How do it? Curtis, is there a way I can increase the font size in this script editor?
Edit menu, increase font size.
Control plus, okay. Okay. So now I've almost got this, and now I'm going to do something a little bit nasty, I think, because we found a glitch in this earlier. So I have to import. Actually, I'm going to do something a little mean, but not totally mean, because I think now I am going to do something mean. Yeah. I just opened up another one, but anyway, what I wanted to do here was Java. Yeah. Okay. From. It's this.
Oh, that's right.
Yeah. So maybe.
But this is the two-edged sword of the fact that all these apps have so many different convenience signatures. It's like I can accept all these different kinds of types. So we have integers versus doubles. Python doesn't necessarily deal well with it.
Okay.
So you sometimes have to get Python fixed.
Yeah. So let's run it. Oh, so we have our thing. We have our S, and I'll make our S super big. And
He ran it before, and it remembered the two.
oh yeah, I remembered the two. So
If you don't want that, you say persist equals false in the params, and then it would always start at 3.
So, does anybody know what happened? I only have like one blob now. So, the width of my filter was just made way too large, and it didn't work.
So at the moment, I would recommend still using that dial. Another way of doing it would be to write a second script and call that script that one. Ideas very well. Just for like the most super complicated
Okay, any questions about that step? Okay, so the next little exercise is to use a different threshold method. So this is a document, really we need the documentation for this. So in the presentation, I reused Curtis's slide, so I have documentation here, I think. And maybe I should get this into here. Oops. That didn't work. So we want to know what threshold methods are available. How do we do that? We browse to, should have a net.imagej.ops. Then we want to look for thresholding ops. So we go down here, and we get a list of all the different types of thresholding ops there are, or all the different threshold. These are really the thresholding interfaces, right?
They've all imported from ImageJ1. I think there's a couple extra ones, and the one called IJ1 is what ImageJ1 calls it, because that's ImageJ1.
Yeah. So these are the actual interfaces. So if you want to look at this gives you a good idea of what's available. If you want to see yeah, so I'm looking for the threshold namespace. Okay.
By the way, if you get really addicted to Java docs, there's a Chrome extension that adds a search bar to any Java doc website. So it's so nice. It adds a little search box to every Java doc site. But the best is to set up fits and do that auto-complete. Brian would have to cancel already.
Yeah. I'm getting convenience here. Yeah, there is.
Everything's
There's
organized by
namespace.
package name, Brian. So ImageJ.ops or net.image.ops.threshold is where it is.
ImageJ.
So if you want to filter by package on the top,
On the top. Okay. Anyway, that's we can just use the we can just use this list to see what threshold methods we have. So if we wanted to change it to say Lee, we just go up here, change this line of code here, and run again. Let's change our, remember the last value I used, which was obscenely large. So we did the workflow again, except we used a Lee threshold. And actually, I have a question right now. Sorry, for you, Curtis. Is there already or going to be a like some way to, like if you know you want to use the threshold ops, and then you want to have a parameter that gives you a list of what threshold ops are available, is the parameter harvester going to be aware of like an op? Like you could actually use an op for the for the parameter.
I think it works now. If it doesn't, I certainly guess. Like
Okay.
you drop down list where you choose.
Yeah.
Right.
Yeah.
Yeah. The only thing you have to type everything with interfaces. So you can you should be able to use ops. Say you need an ops dot threshold.
Yeah.
But choosing which threshold method, I have to think about that. But yes, in principle, dang it. Thanks, Chris.
In principle, there's already stuff in the framework to ask for what are the available implementations of a certain concept or interface and give a drop-down box that lets you choose. So doing that will be easy, in quotes. Might work already, but we have no examples. We'll get to a script that shows that in code, like having an op that uses another op internally. It's quite nice.
Yeah. Okay, thanks. So the final exercise here is add deconvolution as a second pre-processing step. So first thing I'm going to do is, and here's a little trick that I use sometimes, is if you put 3 quotes, it comments out everything. So if you just want to test like your parameter harvesting, you can, or you just want to test the first part of your script, you can comment out the rest of it really quickly and fiddle around with it so you don't get all the outputs and everything generated. So if I want to add a Boolean here. Deconvolve. So if I run this, yeah, so I'm making typos. So I get a nice little checkbox, which allows me to either deconvolve or not. So what I'm going to do is copy this code, because the deconvolution is going to be really close to that format. I'm going to say if deconvolve, and in Python you have to, your if statements are delimited by spacing or tabs. So I'm going to first off, create a Gauss kernel instead of the Laplacian Gaussian. So I'm going to change this. Yeah, I could just change this to kernel here. And then I'm going to override my input. So I'm now going to use, instead of the filter namespace, I'm going to use the deconvolve namespace. And I'm going to use Richardson LOCI. Input data, we just want to use the okay. I'm going to go 10 iterations, and let's see if this works. Let's make sure this guy is highlighted. So I'm going to cancel this, because one other thing I should do here, just to make sure. Yeah. Let's just show it here to see, make sure.
I recommend 4 screens. You have one for your web browser, one for your terminal, one for your Eclipse, and one for your ImageJ. It works really well.
So this code is actually embedded into the presentation. So later, yeah. And let's see if this worked. We have a thresholded, we have Laplacian of Gaussian, and we have deconvolved. So we've added deconvolution with the Gaussian as a pre-processing step, and it really didn't take much code to do that. So that's kind of cool. So yeah, so the code I just used is embedded in the presentation. So later on, if you want to, you can go back to this presentation, just cut out this code and embed it into the original script, and it should run. And if there's any problems with that, like just ask a question on the listserv or some or Gitter. Is there any questions about that that workflow? Okay, so this example shows how to threshold a hyperslice. So this is a really subtle example, because what we're going to do here is we're going to apply a threshold to our n-dimensional data. So we're going to use the same data set, the confocal series data set, and it's x, y, channel, and z. So when we do a threshold, we calculate a histogram, find a threshold, apply it. Now, there's an interesting question here. If we have this 3D plus channels data set, do we want to calculate the threshold based on the image of each 2D slice, or do we want to calculate the threshold on each 3D volume? So ops and ImageLib are written in a way that makes it really easy just to do both, and compare results, try to figure out which one's better, which one makes sense. So let's.
So to be clear, by default, ops thresholding works across your entire ND data set. If you have a 4D data set and you say, I want to take an OTSU threshold, it looks at all pixels across all time, all channels, and makes a histogram of that and does it on that. And so the common case is to threshold each plane. And that's one of the things that this can do.
So yeah, so ops is, that's a really good point, because ops is powerful, but if you're not careful, it can give you unexpected results like that. So you might it wouldn't really make sense to calculate a threshold between channels in a lot of cases, using the data from both channels. So anyway, I closed all my images. I used the Shift W. So I'm gonna start a little bit cleaner, then open samples again, and open up the confocal series image. Now, go to templates, tutorials, and this time we're going to do slice-wise threshold. So in this script, we're going to specify the dimension that we want to process. And by default, that also specifies the dimensions to iterate. So if we say if we have x, y, z, channel, time, if we say process x, y, then it will process each XY unit. It will apply an individual imaging algorithm to each XY unit and iterate through the Z, channel, and time dimensions. And then if we said XYZ, it would process 3D volumes and iterate through channel and time. So I guess we just opened up the script. So the first half of the script just sets up our parameters, sets up some imports that we need, and then prints out our dimensions. So we've actually done most of this before. It's just always a good idea to take a look at what you actually have. Then this is an example of creating an op and passing it to another op. So the code, there's a segment of code that creates the ought-to op. Then it actually creates memory for the output. And these are going to be used as parameters to a second op. So, Curtis, do you want to maybe explain the difference between why computer ops and function ops, and why we are in this case we're creating memory for the output, but we haven't done that before?
Yeah, briefly. Okay, so there are certain subclasses of ops that conform to certain structure, so that they can then be reused by other ops. So, for example, the most common thing is that you have an op that has a particular kind of input and produces a particular kind of output. And there may be other parameters involved, but those are sort of secondary, right? So even something like adding a constant to an image, you can say, well, the image is my first class thing that I want to work on. The fact that I'm adding a constant, I just fix that constant. Leave it fixed. It's sort of like the difference between independent and dependent variables. So what you want to do is loop the same op over multiple inputs, and defining whatever the special input is makes a big difference here for the structure. So for example, we have an op called the loop op, and it takes as input another op and like the number of times you want to loop. And so if you want to add, say you have an image and you want to add it to another image and you want to iterate this 10 times, you run the loop op and you fix the image you want to add 10 times as the fixed input. And then, loop's a bit, okay, loop's a bad example actually.
Slicewise is kind of like that, because slicewise is a loop.
Yes,
Yeah.
There's a loop op, and there's another one called map. Map is like the coolest example, which is I have an op that works on a single number and I want to do it on an image. So that's the number one use case. I should have just started with that. So if you write an op that does something fancy to a single pixel, then you can apply that op pixel-wise across your entire n-dimensional image using the map op. So that's a perfect example here. And in order to do that, make map super general, you just have to make sure that whatever operation you pass into map conforms to these certain requirements of having defining which input is the one that I'm going to be able to vary. Yeah, similar. That's why we named it. Yeah, it's a common name. And that is exactly what Brian is showing. That op is called Slicewise, and it is right there. And yes, perfect. That's why he's bringing this up now, is because it lets you kind of define the subregions.
Yeah, and that's what I'm using right there. The highlighted code. Because we zoomed in here. Let's look at this is the slicewise op here. So we created the op we want to use, which is ought-to. We created memory for the output. Then we call the slicewise op, and we pass it the output memory, the input, the op that we want to use, and then this final parameter specifies the dimensions that we want to process. So in this case, it's x and y. So it means we want to apply thresholding to the x and y dimensions. So again, it took me a long time to sort of grasp all these concepts and get more comfortable with the APIs. So again, all these examples are actually in two places. They're obviously in the tutorials and they're embedded into the presentation. So if you want to go back and look at them after, and then ping all kinds of questions, that's the way I would have to do it. I wouldn't be able to absorb it in 2 hours. So we just ran our little script, and we did a threshold. We did a slice-wise threshold on this data set. So we have an ND data set returned with every slice thresholded. So here's a little exercise, again, to try to demonstrate the concepts we were just talking about. We want to change it, so we want to pass 3 dimensions to the slice-wise op, and then see how the behavior changes. So in this call, in the call to the slice-wise, I'm going to add another parameter. So now this is telling it, the first time I ran it, I was telling it process X and Y, every X and Y. Now I'm telling it process every X, Y, and Z. Let's just make sure I have the right image highlighted. So now we have 2 results. This is the first one. And here's the second. And we're looking at the first slice of each, and they're a little different. Does anybody know why they're different and sort of what happened? So the first time we ran it, it thresholded each, it applied automatic thresholding to each slice individually. So the histograms that the threshold was determined from were made using slice data. The second time, it used 3-dimensional data for the thresholding. So the threshold was actually calculated on the entire volume. So you got a different threshold. You probably got a, in this case, each slice has its own threshold. So it's going to basically threshold more data, more pixels from each slice, because it's not considering the entire range of values in the volume. This time, it used the entire volume, so you get a different result. Yeah, so that's exactly. I think that's exactly. If I understand your question, that's exactly what we're trying to what we did here. So yeah. So when I passed X and Y, it said use each slice. When I passed X, Y, Z, it was like each volume, and then you could actually pass C. And in this time it's the result might not make sense, but this time it's going to use the entire data set. So in this case, this is my result where this result here is the one where I used, I included channel data in the histogram, so we don't get a good result on the green channel because it was using the entire data set to choose a threshold, and that threshold didn't make sense for this slice. Okay. Yep. Yeah, this is using the latest Fiji release. So Fiji is now shipping with all this ImageJ2 functionality. So you should be able to, if you get update to the latest release as of today, you should be able to run all this.
The main caveat here is, well, firstly, all this stuff is part of ImageJ2 core. ImageJ Ops is part of ImageJ2 core, but it comes with the Fiji distribution. So if you have Fiji, you have access to it. The reason we're using scripting languages instead of the ImageJ macro language is because the macro language is the only thing that works differently, and it has its own set of functions that are different than the Java functions. Whereas with scripting, you can basically call any of the Java API functions, including ops. And so that's what we're doing. But ops is not exposed in the ImageJ1 macro language. There's only one way to call other stuff from the macros, and it's this command called call, which can call static methods. So it's more work. Actually, you can also embed scripts in your macro, script snippets, but basically it boils down to writing a script then anyway. So I would advise using anything besides the macro language when you're trying to do things that are this complicated. Macros are nice for very fast prototyping with the recorder right now for simpler things. But if you find yourself with a 1,000-line macro, you should probably stop and say, is this really the best way?
And just to add something quick, the one example we did called this one, the ops threshold IJ1 analyze, once we got to this line of code here, this is an example of how we convert back to ImageJ1 data structures. So from this point on, we can use ij.run and run any macro, like if you have a macro, you can it's not the macro language, but it's using the same namespaces, and you could run your entire macro. Because this is, you don't have, you can, anything that ij.run has, you can do after this point.
Including ij.run macro to run a macro.
So the next example we're going to do is projections. And in this case, we're going to do, it's another one of these sort of more advanced examples, but we're going to use, we're going to create ops, and then we're going to pass the ops to the projection op. So, a projection just sort of reduces the dimensionality of a data set, but you need a strategy. So you can do, if you do some projection, it goes along one axis and adds up all the pixels. If you do max projection, it goes along an axis and takes the max along that axis. So in this example, we're defining the strategy, then calling the projection op. So if we go back to our script editor again, you can use Shift W to close all the images. If you have a lot of stuff open, open up confocal series again, and run the crop one more time, because we want to get a 3D volume to work with. So we can get this should have an image called C0, and this is just a 3D volume, so that's going to be a good image to work with for projections. Then we can open up our templates, tutorials, and the code is right here. Before running it, I'll go through it. Once again, set up parameters, then do some imports. Then we define a dimension to project. And there's a little bit of a tricky step here. So if this won't make sense to you, this line here, unless you have done a little bit of Python. So this line here is actually using something called list comprehension to sort of form a list of the dimensions of our result sort of on the fly. And I've just printed out that in the script so we can verify that it's working as expected. Then we are actually creating memory for our output. Then we use our ops service to create different types of ops, and these are just sort of general ops, like max is a general op that calculates the max, sum is a general op that calculates the sum. In the final step, we pass that to the project op. So the project op takes output memory, input data, the type of op we want to use to project, and the dimension that we want to project along. And we call it twice. We call it once passing a max op and once passing a sum op, and then we display the results. So let me run this. And we should have a max projection and a sum projection. And these are these are good ways to quickly look at all the different structure that's along the third dimension in our data. So a couple of little exercises here. First thing, I want to try projecting in a different dimension. So that's pretty easy to do with this script. The very first line of code, I'm asking the data set, what is the index of the z dimension? So I'm just going to change that, and I'm going to ask it, what is the dimension of the x dimension, And that's going to change the behavior of the script so that the projection is done in x. So if I select my 3D image again, run it. And this time we get the sort of the axial projections, and those are similar to the images I was showing in the deconvolution presentation when I was looking at data along the third axis. And this is, especially for stuff like deconvolution, this is really, really important because, as I mentioned in that presentation, everything often works really great in x and y, and if you just look at your x and y, you think everything's okay, and then as soon as you look at your third dimension, you realize that there might be artifacts, or you might not have the really good reconstruction along that axis. So another thing I'll say about this script, I know I realize that this is really, there's a lot of steps to just get a projection. This is something that will change in the near future. So we were already talking about this a little bit. You really should just be able to say ops.project and pass in your data set and your dimension, and boom, you get it right away in one line of code. And that's going to happen. A lot of the development of this project, it's sort of an exercise in starting from something really, really powerful, but kind of complicated, and then adding simpler ways to access it. So a lot of the work that's being done is with these namespaces and everything is adding more like simpler versions of the op, more signatures in the namespaces, so that you have easier ways to access this functionality. So this one, no question, is going to be next year, or probably maybe even next week, will be much simpler. However, there will always be sort of like advanced functionality that you might want to take advantage of. So learning how to think like in these, like in this way, like passing ops to other ops, is going to be really valuable, because somebody might come up with a new way to project data or a new statistic that you'd like to use for your projection. So there might be simple ways to access like the max projection and the sum projection, but to do this new type, you're going to have to, when it's bleeding edge, you're going to have to go back to the sort of mixing and matching style. So it's as an ops programmer, it's useful to know how to do these types of workflows. So we've got about 10 minutes left, and it looks like we are at the very last example. So this example is FFT template matching with ops and ImageLib2. And this example was actually ported directly from one of the ImageLib2 tutorials, and it's another pretty complicated example. However, the one really useful thing about this is it shows how to use ImageLib2 from a script. So ImageLib2 and some of the plugins that are written using it are really, really powerful. One of the purposes of ops is to sort of access a lot of these little utilities. So like that the TrackMate plugin had a lot of little cool utilities for like reducing noise and pre-processing these noisy, spotty images, detecting spots before doing the tracking. But it was, before ops, it was possible to use them in a script, but harder. So the purpose of ops is really to simplify. However, we can still use like lower level interfaces in scripts. So if we find some like lower level code that looks really cool and we want to put it in our script, we can port that to Python. This is sort of an example. First off, how to use FFTs in ops, and second of all, how to use ImageLib2 code. So if we go to our script editor, we go to the templates, go to tutorials, and go to find template. So you should see this script. Again, it's in two places, embedded in the presentation and in the tutorials. First step, same as the others, set up parameters and imports. Then we use ops to perform an FFT. This is there's actually a question that gets asked on the listserv quite a bit. People want to know how to do FFTs. So there are some ops for FFTs. In this example, I have sort of a basic FFT call with no parameters, and then I have a more complicated looking call. So if you have worked with FFTs before, you'll know that there's, when you're doing any kind of filtering, you have to sometimes precondition your images. You have to choose a strategy to deal with boundary pixels. FFTs work much faster at certain sizes, especially powers of 2, but there's some other convenient sizes. So when you're doing an FFT, if you're ever looking at the underlying code, it actually, a lot of times it actually, in the code, it actually resizes the image a little bit, so it ends up being one of these faster sizes. So there's a lot of little obtuse little details, and the complicated call sort of gives you control over like your boundary sizes and whether you want to expand to a fast size, what kind of edge extension strategy you want to use. And if you don't want to worry about all that and just have it choose defaults, you can use the simple call. Then there's a utility in, I think it's an ImageLib2 utility as well, that allows us to visualize the results of the FFT. So these FFTs are complex.
Just to elaborate quickly, that function predates ImageJ2. It's existed when ImageLib2 was just embedded inside ImageJ1, essentially. It was a little viewer. And it also, so the reason we're still using it instead of that UI.show call that we're using everywhere else is because this thing is smarter about complex numbers, basically.
Yeah. So this thing will show like your phase.
For now.
You can look at your real and imaginary parts. And so we perform this FFT. Then, the purpose of doing FFTs is because then you want to do some math or some calculations in the Fourier transform domain. So that means we have to deal with complex numbers. So this snippet of code here is using, it's basically ImageLib2, and it's using ImageLib2 types. And this is like an ImageLib2 interface that allows us to deal with any type of number, and it has little utilities to deal with complex numbers and do complex math and all kinds of other things. But if you ever look at ImageLib2 code, you'll see like a lot of little loops like this, this is meant to be really generic. This is how it gets, if I'm correct on this is how it gets its ability to deal with almost any type of number, because you're just writing. These. If you ever look at the design of this, which is really great, there's like a huge type hierarchy. Maybe sometime it'd be great to have an ImageJ2 talk at one of these things. I think just to learn more about all this stuff. But anyway, the final thing we do here is we take an inverse transform and show our result here. And this algorithm is a template matching algorithm. So what it's trying to do here is take a subimage and find its location on a bigger image. So
since we've only got a couple minutes,
okay,
we should probably just show it. And
yeah, so we'll just show this. And the other thing you're going to get to see here, somebody asked this question earlier, if you have two images, it lets you choose them. So I'm going to choose. Okay, I actually don't see
the title is wrong.
yeah, I'm not sure if I.
You close down your extraneous images.
Just very quickly see if I can. Here they are. Maybe I just lost it somehow. So this is just a little sort of toy example, but it tries to find a template in a bigger image. And in this case, the template was cropped directly from the image, so it was pretty simple. I'm not sure how well this strategy would work on general images. But the main point of the example is just to show you a little bit about how to work with FFTs. Then you get all the different power spectrum, phase spectrum, and the imaginary numbers. So anyway, we're pretty much out of time. That's the presentation, the tutorial.